In part 2 of our lesson on curve sketching, we will go over the guidelines for graphing. Step 1 is to determine the domain. What are all the allowed values for x that can be used in your graph? Step 2, find the intercepts. Solve f of x equals 0 to get the x-intercepts. Evaluate f of 0 to get y-intercepts. Step 3, find all vertical, horizontal, or slant asymptotes. Use appropriate limits to determine the behavior of the graph as it approaches the asymptotes. So a quick review here. Vertical asymptotes occur when the denominator is equal to 0 and we look at a one-sided limit that goes to infinity. Either plus infinity or minus infinity, either one. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. When that condition exists, we have to do the limit as x goes to positive infinity of f of x and the limit as x goes to negative infinity of f of x. If either of those limits results in a real number, then we know y equals L, that real number, is a horizontal asymptote. Slant asymptotes happen when the degree of the numerator is exactly one more than the degree of the denominator. If that condition exists, then you do the polynomial long division and see if you get a remainder. If you do, then the quotient that results gives the slant asymptote. Step 4 is to identify any extrema. You find f prime of x and make a sine graph. Use the first derivative test, or you could use also the second derivative test, to identify relative minimums and maximums. And of course you need to label any extrema with their xy coordinates on the graph. The last step is to identify any points of inflection. So you'll find f double prime and make a sine graph. Look for changes in sign, then label any points of inflection with their xy coordinates on the graph. So let's get started with an example. In this example, we want to use the guidelines for graphing to sketch the graph of this given f of x. First off, we want to consider the domain, and we know that x cannot equal 2, which means that our domain is from negative infinity to 2 union 2 to infinity. So we're going to have curves on the graph everywhere except at x equals 2. Next, we find the intercepts, and for the x-intercepts, we know we take our function x squared minus 2x plus 4 over x minus 2, and we set that equal to 0. Well, the only place that a rational expression can equal 0 is if its numerator is 0 while its denominator is not 0. So let's look at solving this numerator equal to 0. It does not factor, so we are going to need to use the quadratic formula. So for x squared minus 2x plus 4 equaling 0, we get that x is equal to negative of negative 2 plus or minus the square root of negative 2 squared minus 4 times a times c over 2 times a, which is 1. Now, if we look inside this square root, we have 4 minus 16, which of course is negative. You cannot take the square root of a negative, so therefore there are no roots. Now for the y-intercept, we know we have to evaluate f of 0, so that would be 0 squared minus 2 times 0 plus 4 over 0 minus 2. So we have 4 over negative 2, which is negative 2. So we find out that we have a y-intercept of 0, negative 2. Next up, we will need to look at the asymptotes. Vertical asymptotes occur when the denominator is 0 and we get infinity or negative infinity for the one-sided limits. So we are going to look at when x is equal to 2. So the limit as x approaches 2 from the right of x squared minus 2x plus 4 over x minus 2. If we plug 2 into the numerator, we get 4 minus 4 plus 4. If we plug 2 into the denominator, we get 0, and because this is a one-sided limit, we have to decide if this is going to be 0 plus or 0 minus. Since we are coming into 2 from the right, that means we are thinking of numbers bigger than 2, like 2.00001, and then if we subtract 2, we're going to get a tiny little positive. So we have 4 over 0 positive, which is going to go to positive infinity. So therefore, we have a vertical asymptote at x equals 2. And furthermore, we know on the graph that at x equals 2, when we are coming into 2 from the right, the graph will go to positive infinity. So we know it's going to go up over here when we're coming into 2 from the right. Now, if we look at the limit as x approaches 2 from the left of x squared minus 2x plus 4 over x minus 2. Of course, the numerator, we know already, is 4. The denominator will be 0, but when we plug in a number approaching 2 from the left, we're going to think 1.999 over here. If we put 1.999 in here and subtract 2, we are going to get a tiny little negative. So this is going to go to negative infinity. And that means as x approaches 2 from the left side of 2 on the graph is going to head down to negative infinity. So as we come into 2 from the left, the graph is going to be heading down to negative infinity. And this is why you have to do both one-sided limits, because you don't know which way the graph will be going unless you do that. Next, we will check for horizontal asymptotes. And remember, the condition we need is for the degree of the numerator to be less than or equal to the degree of the denominator. But in our case, the degree of the numerator is 2, the degree of the denominator is 1. So for horizontal asymptotes, we are going to say none, because the degree of the numerator is greater than the degree of the denominator. Now we can check for slant asymptotes, and we know the conditions needed for that is that the degree of the numerator is exactly 1 more than the degree of the denominator, which is the case we have. 2 is exactly 1 more than 1. So that means we go on to check the polynomial long division, and we have x minus 2 will divide into x squared minus 2x plus 4. So we are going to need to multiply by x, because we have to get that x squared there. So x times the quantity x minus 2 will be x squared minus 2x. We subtract, and now the x squared minus x squared cancels out. The negative 2x plus 2x cancels out. So we bring down this 4, and that is our remainder. So then that tells us we will have a slant asymptote at y equals the quotient, which is x. So now our next step will be to get these two asymptotes on our graph. We have a vertical asymptote at x equals 2, and we have a slant asymptote at y equals x. We can put our vertical asymptote of x equals 2 on the graph. And we know that as x approaches 2 from the right, the graph is going to positive infinity, and as x approaches 2 from the left, the graph has to go to negative infinity. We also had a slant asymptote at y equals x, so we draw a line whose slope is 1, and this is our slant asymptote. Now we have to find the derivative and use it to find any relative minimums or relative maximums. Now we know that f of x is x squared minus 2x plus 4 over x minus 2, so that means we are going to use the quotient rule to find f prime. So the derivative of the top is 2x minus 2 And we take that times the denominator, x minus 2. Then we have to subtract the numerator, x squared minus 2x plus 4, times the derivative of the denominator, which is 1. And then we will take that over the denominator squared. Let's simplify. Foiling this out, we get 2x squared minus 4x minus 2x plus 4, and then distributing this negative sign into all three terms, we get minus x squared plus 2x minus 4. We still have our denominator of x minus 2 squared. We continue to simplify. In the numerator, we have 2x squared minus x squared is x squared. This minus 2x will cancel with this plus 2x, so we bring down minus 4x. And this adding 4 and subtracting 4 will cancel out. We bring down the denominator, x minus 2 squared, and then we're going to need to factor the numerator. So now we have x times x minus 4 over the quantity x minus 2 squared, and we will set that to 0 and does not exist. Now this rational expression will equal 0 at x equals 0 and x equals 4, and it does not exist at x equals 2. And it's a really good idea to remind yourself that you already know that that is a vertical asymptote. So it's never going to be a minimum or a maximum because it's already a vertical asymptote. Now let's put those values on our sine graph. We have 0, 4, and 2. So 0, we know the derivative is 0 there. At 2, we know that the derivative does not exist there, and it is a vertical asymptote. And at 4, we know the derivative is 0 there. Now we can do our sine analysis. So in this region, we can pick x is negative 1. Now the denominator is always going to be a positive because of that squaring, so I'm not going to plug in any values there. So I will only plug that negative 1 into these two factors in the top. So we have negative 1 in here makes this negative. Negative 1 in here will also make this negative. So that means the derivative is positive and the graph is increasing. A test point here would be 1. I would have a positive times a negative is a negative, so f is decreasing. A test point here would be 3. Positive times a negative is a negative. Again, the graph is decreasing. So something to notice here is it does not always change just because there's a critical number there. And then finally, a test point over here would be 5, and both of these factors are positive, so the graph is increasing. Now, by the first derivative test, the derivative is changing from positive to negative at x equals 0. That means we have a maximum there. And over here at x equals 4, the derivative is changing from negative to positive, so that means we have a minimum there. Now we already know that we have a y-intercept of 0, -2. So that means we already know f of 0 is -2, and that's going to be a max. Now we need to figure out f of 4. So f of 4 is going to be 4 squared minus 2 times 4 plus 4 over 4 minus 2. So we have 16 minus 8 is 8, plus 4 is 12, divided by 2 is equal to 6. So we have a relative min at 4, 6. So we come over here to the graph, and at 4, 6, we make a note that we have a minimum there. Now it's time to look for any points of inflection on the graph. So we're going to need the second derivative. Now I'm going to recommend when you work on the second derivative here that rather than using this form of the derivative, which would be more complicated because we're going to have to use the quotient rule, but then when we find f prime, we'd have to use the product rule. So I'm going to choose instead to use this form of the derivative when I work on the second derivative. So then the derivative of the top is going to be 2x minus 4 times the bottom, quantity x minus 2 squared, minus the top, x squared minus 4x, times the derivative of the denominator, which is going to be 2 times x minus 2 to the 1, and then chain rule would say times 1. And then we have to take the denominator, which is quantity x minus 2 squared, and square it. Continuing to simplify, we see the denominator is going to be x minus 2 to the 4th power. Now, looking at the numerator, there's a lot we would have to multiply out, but notice that we have an x minus 2 squared here, and we have an x minus 2 here. Let's go ahead and factor that out right now. Then that means on the inside we would have to FOIL out 2x minus 4 times x minus 2. So let's go ahead and FOIL these two right now, because remember we factored out one of these, so this really isn't squared anymore. So first times first, we get 2x squared, outer times outer, minus 4x, inner times inner, minus 4x, last times last, plus 8. Now, over here, we've already factored out that x minus 2. That's right here. So then we just have to take this 2, which is really negative 2 because of that minus sign, and multiply it into each of those two terms. So we have a negative 2 x squared, and then we have a negative 2 times negative 4x, so we add 8x. Continuing to simplify, this x minus 2 is going to cancel one of those. So now we have x minus 2 to the third in the denominator. In the numerator, a whole bunch of stuff cancels out. 2x squared and minus 2x squared cancel out. Minus 8x and plus 8x cancel out. The only thing we have left is this 8. And now here, we have to set this to 0 and does not exist. Now this rational expression, there's no value that we could put in for x that would turn the numerator into 0, so this is a never. And down here, we know it does not exist at x equals 2, but again, let's remind ourselves that is a vertical asymptote. Now let's go and fill in our sine graph for f double prime. First, we have to line up the x equals 2 with the other one. We know the second derivative does not exist, and we know there's a vertical asymptote there. Now let's work on the sine graph. We can plug in x equals 0 as a test point here. If we plug in x equals 0, then we have a negative 2 being cubed, which is negative. So that means the graph is concave down there. Over here, we can plug in x equals 3 as a test point. And if we plug in x equals 3, the second derivative will be positive, so the graph is concave up. And now we are ready to work on the combo chart. Remember that we're going to put any value for x that appears in either chart. So we have to put x equals 0, which we know is a max, x equals 2, which we know is a vertical asymptote, and x equals 4, which we know is a min. Now, from negative infinity to 0, the graph is increasing and concave down. So we know that that's going to have to look like this. Then from 0 until 2, the graph is decreasing and concave down. So that would have to look like this. We know there's going to be a vertical asymptote here separating things. From 2 until 4, the graph is decreasing and concave up. So that has to look like this. And then from 4 until infinity, the graph is increasing and concave up, which looks like this. Now, our job is to tie in what we know the basic overall shape of the graph is with the asymptotes and intercepts and mins and maxes that we have on the graph. Now, from negative infinity until 0, we know the basic shape of the curve is increasing and concave down. However, we have to make sure that that works also with this slant asymptote we have. So it's going to look like this, has to approach that asymptote. Then from that max until the vertical asymptote, it has to have a shape of decreasing and concave down. which ties in with what we already knew, where the graph would have to be going to negative infinity here. Then from 2 to 4, it's decreasing and concave up, which would be this shape here. And then from 4 on, it's increasing and concave up and has to approach the slant asymptote. So now we can see we have a good look with a lot of detail at this graph.